just have her show you as well. Okay, so a term that we need to be aware of is intramolecular forces. And you're going to hear me kind of emphasize these terms because the terms are similar to one another. An intramolecular force is a force that holds atoms together in one molecule. Remember on the reading guide, question number 4 for homework today, what's a chemical change? You change what the substance is. If you break an intramolecular force, you're making it into something new because you're breaking chemical bonds. That could be for something that's ionic, breaking apart the Na from the Cl. So no longer do you have sodium chloride, you just have sodium, you just have chlorine. It could be breaking apart the polar covalent bonds within water. So instead of H2O, you have hydrogen, you have oxygen. It could be breaking apart nonpolar covalent compound bonds. Example I have there is fluorine, a diatomic element. I want to keep on reminding you about the diatomics because a lot of us don't really know them still or forget them very easily. Point of this first page, we got to remember last unit. We got to remember semester 1. We have to know our bond types. Now, as I go over notes, I'm relatively going to just dismiss metallic bonding because metals are usually made of just one component, the same metal over and over again, unless you make what's called an alloy. So if we heat them up, we're just changing their state of matter. We're doing a physical change. We're not actually changing what they're made up of. Although some metals, you heat them up enough, they can start reacting with the air in the room. We used to do a lab where we heat up magnesium so much it would turn into ash and magnesium oxide. Are we okay on page 1? Okay. This was intramolecular. What holds the atoms together within one compound? Intermolecular is what holds two separate molecules together. For the most part, the intermolecular force, what holds two molecules together, is not as strong as the intramolecular force, what holds the atoms together in one compound. There is an exception, however, that'd be NaCl. What I'd like to do is I'll give you a second to write down this, and then I'm going to switch over to the Smart Notebook to kind of draw out the example. As part of what the notes are is, yes, reminder of the terms you had on page 1 of the packet, but also the notes are meant to be, here's a couple kind of Lewis dot examples to hopefully drive home this point. All right, so remember when we did Lewis dot, Na plus Cl minus. I'm going to omit the electrons around the chloride. Yes, I should put 8 dots around it if I, fine, I'll do it. There's the Lewis dot sodium chloride. An ionic compound, when you do the formula for it, when you do your naming problems, it's the simplest ratio of metal to nonmetal. Because what an ionic compound is when you find it in nature, like when I put, yes, hold on now, when I put the salt on top of the lid a minute ago and tried to melt it, an ionic compound is just a repeating NaCl, NaCl, top, bottom, left, right, forward, back. It's just NaCl over and over again. So if this is one sodium chloride, this could be a second sodium chloride. And on that last slide of notes, the attraction between sodium and chlorine right here. So what's holding Na plus to Cl minus is the exact same thing that's holding this NaCl number 1 to this NaCl number 2. The reason why ionic compounds have such a high melting point is they have full attraction, positive and negative, attracted to each other over and over again. Now this is different than covalent compounds, which again I'll draw the Lewis dot in a little bit for, but I want to make sure we understand that point. So do we have questions on that? All right, so let's go back then to the slide. If you break an intermolecular force, you're changing the state of matter. Because you're loosening it up. You're changing it from a solid to a liquid or from a liquid to a gas. Therefore, you're not changing what it is. You're just changing the state of matter. That's a physical change. Question 1 from the reading guide. And my main point to finish off this slide, and something that was on that packet that I need us to understand, the intramolecular force, whether something's ionic, polar covalent, or nonpolar covalent. The intramolecular force determines the intermolecular force, what holds one molecule to another. My next 3 slides then are just going to go over the 3 intermolecular forces that was mentioned on that packet that you did. Ready? Our textbook calls it dipole interactions. Some texts will call it dipole-dipole. I'll accept either vocabulary. So you'll notice as we go over notes here, sometimes the vocabulary is a little different between things. Here's me defining dipole-dipole interactions. It's a strong intermolecular force between polar molecules. And why is there that attraction? It's because in polar molecules you have partial charges. So the partial end of one molecule can attract to the other. And once again, in a minute here, I'm going to go back to the Smart Notebook sheet and draw out an example to show you. The example I'm going to use is hydrogen chloride, HCl. So I'll wait until you're all done with this, and I'm going to do a couple quick loose dot drawings again. Okay, Lewis dot for hydrogen chloride. Chlorine is one of the most electronegative elements on the periodic table. It's going to share electrons unequally with hydrogen, which is why this end is the partial negative end, this end is the partial positive end. What holds one HCl to a second HCl, so here's a second HCl, is the fact that I have a partial negative end attracted to a partial positive end. This dotted line is representing that dipole interaction, or what my notes just call a dipole-dipole interaction. Sometimes it's called dipole-dipole because this partial negative is called a dipole, this partial positive is called a dipole, so it's attraction between 2 opposite ends. Notice how these attractions are between partial positive and partial negative. If you have opposite charges, they attract one another. What you were taught in elementary school about opposites attract still holds true today. But these aren't big opposite attracts. These are partial opposite attracts. Okay, so that is dipole-dipole, or just dipole interactions. Depending upon what text you would read, it would give a different name for it possibly. Next, we're going to go over hydrogen bonding. Hydrogen bonding is a specific type of dipole interaction. It only occurs in 3 instances. Molecules that contain an HO bond, molecules that contain an HF bond, or molecules that contain an HN bond. So it's a type of dipole interaction, but it's stronger. than a normal dipole. I think Tristan was the one who gave us the order of strength on page 1. Hydrogen bonding was stronger than dipole interactions. So it's a specific one in that category. It's just the best one in that category. And again, once you get this down, I'm going to draw the example of water, which maybe we drew on our model behavior packet to start class, although some of us really weren't sure on that. A lot of water's characteristics can come back to the fact that what holds one water molecule to another is hydrogen bonding. So if I draw the Lewis dot for a water molecule, I'm purposely drawing my partial symbols larger in this example than in the previous example. Because since water is really polar covalent, it's more partial positive and more partial negative. A hydrogen bond is the attraction from the partial positive end of one to the partial negative end of the other. So again, this dotted line right here is the hydrogen bond. Some students have mistaken it to be the covalent bond that occurs between hydrogen and oxygen. Hydrogen bond is referring to what's holding one water molecule to another water molecule. That's why it's an intermolecular force. But
I thought hydrogen couldn't be like bonded twice.
this dotted line here is not a covalent bond. So you're correct. Hydrogen only with one electron can only bond once. And right here is that polar covalent bond. This is an attraction right here between the partial positive end and the partial negative end, which is kind of why we do it with a dotted line instead of a full line. The dotted line is trying to more show the attraction. A full line is the actual covalent bond, like you're thinking. Now, our textbook, our current textbook refers to it as London dispersion forces. The reading that you did today and the packet that you did just calls it dispersion forces. There's a scientist named London who wanted his name attached to something, so this is what he attached it to, and apparently some people no longer feel like we should put his name on it. Dispersion forces are the weakest interaction. They create what's called temporary dipoles, and probably when I draw this out in a smart board, it'll help out in a minute to explain what that means. But this occurs in non-polar molecules. And that's one of the keys here, is it occurs in non-polar things. So dipole interactions and hydrogen bonding both occur in polar molecules. Dispersion forces actually occur for everything, but it's all that non-polar has to hold it together. What can happen is we create temporary attractions for a split second, which is why if you're a larger nonpolar, you can have a lot of these temporary forces. Smaller nonpolars have very few. Think about the gases in this room. N2, which is nitrogen, nonpolar. O2, oxygen, nonpolar. Very small nonpolars at that. So they are gases, even with room heat. Another gas is carbon dioxide, and I'm going to draw that example up on the smartboard. So again, we'll give you a second to catch up with this, and then I'll draw this out. I actually do have 2 more slides of notes, but with this class right now, this is probably where we're going to have to end after I draw it out, just because we will be done soon. So we'll just start the last 2 slides and notes next class period. Carbon dioxide. Carbon dioxide is a non-polar covalent molecule. If you're non-polar, you're sharing electrons relatively equally, which means you don't have a partial positive and partial negative end. So unlike the previous problem with water, where there was a partial positive and partial negative, or the HCl where there was partial positive and partial negative, or the NaCl where there was a full positive and negative, there's nothing to attract. And if you can't attract, you can't hold it together. However, when I drew these dots, those are electrons. Electrons are constantly orbiting a nucleus. Let's say for 1 split second, these 2 electrons start orbiting towards the top. For a split second, that would make this kind of positive, partial positive. And let's say for a split second, these electrons rotate here. For a split second then, that's kind of negative. Now I do have opposite charges that can attract. This is the dispersion force. The problem with that is just as soon as that forms, it goes away, because then the electrons rotate again. Well, maybe the other side of the molecule, maybe over here it can do the same thing. Nonpolar without true partial or full charges has a hard time attracting to other nonpolars. And that's why then they're usually a gas at even room temperature. Room heat's enough to make that happen. Now, like I said, I have 2 more slides, but for you guys, we are going to stop. So continuing on, a couple of keys that we need to be aware of. State of matter is a balance between 2 things. It's a balance between the forces holding things together, so the attraction, and the amount of kinetic energy. And as I have for the first bullet point, the higher the temperature, the greater the movement. The faster things are moving, the more difficult it is to hold them together. Again, I like using the example of you sitting in your desk. It's easy to hold you in place when you're not moving around a lot. But if you guys are moving around a lot, you start moving throughout the lab benches, you're no longer in a solid, fixed position. The greater the intermolecular force, the more likely you can still be a solid even if you heat things up a lot. Think back to the demonstration I just gave before with the salt and the sugar. Salt is ionic, held together by full charges. Adding heat kept it still a solid. Sugar, polar covalent, held together by partial charges. Heated up, it melted. General rule of thumb when we look at room conditions, ionic compounds and metallic, although this is more focused on ionic. Ionic compounds are a solid at room temperature. Pretty common that polar covalents could be liquids, and nonpolar covalents, especially if they're small, are a gas. Because ionic is held together by full charges, a lot of attraction. Polar covalent is held together by partial charges, some attraction. Nonpolar, really no attraction. Those temporary dipoles only last for a split second. So less attraction, doesn't take much energy to break it apart. An analogy I like to use, and you don't actually have to write this down, an analogy I like to use is dipole-dipole, or again, just dipole interactions, and hydrogen bonding is like a rope holding 2 people together. If it's a thick rope and they're both holding on tight, it's very easy for them to hold on to it. A dispersion force is like a piece of thread. It's much weaker, it's much smaller. So if we had 2 individuals in this room, each holding one end of the thread and started walking around, that thread could break pretty easily unless they move really slow. One thing to mention about that, however, is the larger the molecule is, the more dispersion forces that can occur.
So again, if we think about what holds things together in their states of matter, we have to consider how fast they're moving. Fast things are more likely to be a gas. Slow things are more likely to be a solid. But we also have to think about how they're being held together. If they're held together with a weak attraction, like a dispersion force, that's like one single thread holding two individuals together, even if you're moving slow, it still might break. But if you have hundreds, if not thousands of threads, either because you're a large nonpolar, so you have a lot of dispersion forces, or if you're a polar with the dipole interaction or hydrogen bonding, then you got to be moving faster in order to break you apart. So the goal of lecture here is to combine the ideas of the amount of attraction and the amount of heat that plays a role in the bond type or in the state of matter.